Okay, good morning, everybody.
Good morning.
All right, take out your calculators and your periodic tables, and you should have this worksheet that I put out there. We're going to go through this problem. We're going to work this problem a bunch of different ways here right now and get familiar again with this and get familiar a little bit more with some terminology. Thank you. A couple of you got up here and got the molar masses. All right, we're dealing with this equation. This isn't exactly the equation I worked with the other day when we were pretending we worked at Alcoa. It kind of looks like it, but because it's starting out with aluminum oxide. But in this case, it's aluminum oxide reacting with iron, and the iron is replacing the aluminum to produce iron oxide, iron 3 oxide, ferric oxide, and aluminum. So that's what's going on in this reaction. And the question here is, if we had 50.8 grams of aluminum oxide and it reacted, now you'll see this kind of terminology in these kinds of problems. It's reacting with excess iron. What's that telling you? Well, it's telling you there's plenty of iron here to react with that 50.8 grams of aluminum oxide. There was only a little pinch of iron. The reaction, that we wouldn't consume all that 50.8 grams of aluminum oxide. The reaction would proceed until the iron was gone, and then the reaction would stop. You follow me? But where they're telling us here, there's plenty of iron. Iron is not going to stop this reaction. It's the aluminum oxide that is going to run out. And so then how much, the first thing here is determine the number of moles of aluminum that could be produced. So that's our first problem. There's going to be four or five problems we're going to address from this equation right here. And they're all laid out on these sheets of paper that you have. So determine the number of moles of aluminum. So the pathway we need to go on for part A here is we have grams of aluminum oxide. We're going to have to convert that into moles of aluminum oxide, and then what are we going to have to do? Well, we have to convert it into moles of aluminum. This is just the general path we're going to be on. But before we can calculate how many moles of aluminum this will be produced here, we have to figure out how many moles of aluminum oxide would be produced. Okay, let's back up a little bit further here. What's the first thing we have to do before we can actually address this problem? What would they? Balance and molar mass. Okay, we got the molar mass. We have to balance the equation. We have to find out what the relationship is between moles of aluminum oxide and everything else in the equation, but particularly aluminum. So let's balance the equation. Okay, how do we balance the equation? Go ahead, Daniel.
I got 2 aluminum oxides, 4 iron, 2 iron, and the 2...
two aluminum oxides, 4 iron.
And I got 2 iron on the ferrous oxide.
Iron oxides.
And 4 aluminum.
4 aluminum. Is that right?
You can just put a 2 in front of the F again and a 2 in front of the echo.
Yeah, I put a 2 and then the iron and 2 and then
Oh, okay. Okay, so that's all you needed.
Yeah.
All right. Well, Daniel, yours is balanced. But you can see every one of your numbers is divided by 2, can be divided by 2. And so if you did that, you divide 2 by 2, you get 1. Divide 4 by 2, and you get 2. Divide 2 by 2, and you get 1. And you divide 4 by 2, and you get 2.
Would it be wrong if you left it like that?
Well, I would rather see it this way.
More simplified?
Simpler.
On the exam, in the past, on the exam, I have not counted off if you left it that way. But you should take a look at your coefficients, and if they can be reduced down to a smaller integer, all of them, do that. You can't just divide one of them by 2. They got to all be divisible by 2 to do this. All right, so now it's balanced. It just so happened that aluminum oxide, Al2O3, and its iron oxide, Fe2O3, they're in the same. So the oxygens are already balanced. There's 3 oxygens on both sides of the equation. All right, so now we got it balanced. And what that is telling us right there is that there is a ratio of 1 mole of aluminum oxide will produce 2 moles of aluminum. That's what those coefficients are telling us. All right, so let's follow this path right now. And what we have here is that aluminum oxide is 101.97, is that, no, 96 grams per mole. So where do you start with a problem like this? You start with what you're given. I mean, you have to start with a balanced chemical equation. But now we're going to start with what we're given. And this is what we're given. That there is 50.8 grams of aluminum oxide reacting. And where we want to go here is moles of aluminum. So that's the path I've laid out. We're going to convert the grams of aluminum oxide to moles of aluminum oxide and then get 2 moles of aluminum. All right, so to get this, I need to put grams. For that molar mass, I need to put the grams of the molar mass down here and the mole up here. All right, and that gets me to moles of aluminum oxide. That's not my answer. What happened? How did that move? How did that actually move? That's funny. It moved the slide, but it didn't, I don't know, it didn't move everything together. Sorry about that. One mole aluminum oxide, 101.96 grams of aluminum oxide. Okay, now if I want to convert moles of aluminum oxide into moles of aluminum, how do I use that factor up there? Where does the moles of aluminum oxide go? In the denominator. So 1 mole of aluminum oxide, so there's 2 moles of aluminum going to be produced for every 1 mole of aluminum oxide that reacts. And that gets me to moles of aluminum. And what's that answer? 50.8 times 2 divided by 101.96. Yeah. Yeah. There are three significant figures right here.
But can we just round up? It's like 0.996. So like, can we just round up to 1 mole? Or does it have to be 0.996?
I would say 0.996 for the three significant figures. Is that what it is? 0.996 moles? All right? That's how many moles of aluminum you would produce from 50.8 grams of aluminum oxide. Okay, now let's go on and look at part B here. Determine the grams of aluminum produced in the reaction. Grams of aluminum. Now to get to grams of aluminum from 50.8 grams of aluminum oxide, what are you going to do? You're going to go grams of aluminum oxide. You're going to convert that into moles of aluminum oxide. You're going to convert that into moles of aluminum. And then you're going to have to convert that into grams of aluminum to get your answer. Now step back and look at that and think about that for a minute. Part B.
Just use everything.
Okay, Mark. Mark's looking at it and saying, well, hey, look at this. For part B, we have to do everything we did for part A to get to here. We already got to there. Follow me? I mean, we can, and I will maybe set that up there in a second. But if we already know this, we can just go from here to here, right? Everybody with me? It is being presented as another problem, but it's just the next step in our problem. And I wanted to stop right there. I wanted to do this in two parts here because sometimes you will be asked a question, just this, how many moles of something's going to be produced? That's what, so read and take note of what it is asking you. What does the problem want you to answer or find out? Here we could stop right there. That's the answer. But now for part B, we can actually start right there. Why? Because we're talking about the same amount of aluminum oxide in part A and B. And 50.8 grams of aluminum oxide produces 0.996 moles of aluminum. Now this is a simple moles to grams conversion, right? And what do you need? What is the critical thing you need to do a moles to grams conversion? The molar mass. And there we have, now in this case, we're going to put the mole of aluminum down here. And say there's 101.9. Oh, no, I'm sorry. Whoa. We don't need this molar mass, do we?
No, we just need the single one.
Yeah, I was getting ahead of me here. We just need what is the molar mass of aluminum, and that comes right off the periodic table. All right? 26.98 grams of aluminum per mole of aluminum. So how many grams of aluminum is that?
26.87.
How much?
26.87.
26.87. 87?
Yeah, well, I just rounded it
Oh, to 9? Okay. 26.9, that's fine. Okay, I said this last Thursday. I don't want you to go into this exam, sweating bullets over significant figures. Okay? That's not the heart of this exam. It's a part of it. There will be problems on this exam that says, I'll give you a number, 15.875, and it'll say, how many significant figures are in this number? Okay? 5 significant figures. So there is going to be some questions that question your understanding of what is a significant figure. But when we get into a major calculation like this, if this thing is worth 5 points, I might take a half a point off if you don't get the significant figures right, or maybe we'll see what we do there. But I'm going to give you the majority of the credit, whether you give me 26.87 or 26.9. All right? And I'm going to just really quickly, if you started all over right from the beginning, you'll get the same answer. There's 1 mole of this, 101.96 grams of aluminum oxide. We have to put down there, you get 1 mole, you get 2 moles of aluminum for every 1 mole of aluminum oxide, and then that's getting you 2 moles of aluminum, and then you have to multiply by 26.98 grams of aluminum per mole of aluminum, and you're going to get grams of aluminum. Okay, so if you compare this to that up there, you can see that all the way over to here, it's the same problem. And if you did that calculation, you should get a number like 26.9. Okay? Okay, let me introduce one other term here. Theoretical yield. Theoretical yield. This would be the theoretical yield, 26.9 grams of aluminum. In other words, in theory, or in a perfect world where this reaction went completely to the end, there wasn't any aluminum oxide that didn't come into contact with iron to get reacted. I recovered every single little bit of aluminum that was produced. None of it got lost anywhere. That's the absolute most aluminum you can get out of this reaction. That's theoretical yield. What happens in real world? You never get that much aluminum out of this reaction. It will always be less than 100% yield. If you got 26.9 grams, you did this reaction and you got 26.9 grams, you would do a calculation like this. You'd say, this is what I actually got. This was my theoretical times 100%. I got a 100% yield. This is like acing the final exam. Okay? You got a perfect score. Didn't miss a thing. That's theoretical yield. And so whenever you, any of these problems here where it's saying, okay, how many grams of this would be produced? It's saying in theory how many grams would be produced. I worked for a corporation for a couple decades. We never got theoretical yield. You know, it was always 95% or 93% or 97%. I mean, we were trying to get as close. We didn't want to waste anything. We were trying to get there, doing everything we could to try to get this reaction to go to completion and recover every gram of it that we made. We don't want to waste stuff. We could sell it. But we never got 100% yield. Okay? No one ever does that. In the lab, whatever. So that's theory. That's what we mean. This is the theoretical yield. I just want to introduce that. Okay, let's go on to the second problem. This is the same equation. Same equation, same amount of stuff we're starting with, but we're asking some new questions here. Determine the number of moles of iron oxide. And this is ferric oxide, iron 3 oxide, that would be produced. So the part C here, so we got A and B we already did. Now here's part C. You go ahead and do that. Set this problem up and figure out how many moles of aluminum oxide would be produced. Oh, remember we had it balanced here. Get done with C, then look on to D. Let's see how you would go to D. I don't know what the answer is, but that looks good. Yeah, you got the right factor there. Good. And that I look at that for, is that a realistic number? Look at that's about half of that number. Mm-hmm. So that's realistic, okay? That's almost 0.5, so. When you got that all the way to there already? Okay, now. You have an equal sign right there. Do you mean that?
Well, I just don't know what to put there.
What?
I wouldn't know what to put there.
Okay.
Is it just like that?
Well, you are
that?
dividing that by that, right? This is all on this one side, same side of the equation, right? Mm-hmm. So you're just taking that and dividing it by that. So this isn't equal that. It's part of the problem. Mm-hmm. See up here, you put a times.
Mm-hmm. Well, I don't
yeah. Know. Okay. So remember, where do you start? Start with what you're given. You're given 50.8 grams of aluminum. We're going to go from aluminum oxide. We're going to go from grams of aluminum oxide to moles of aluminum oxide to moles of iron oxide. Okay? I just kind of like that. This is kind of the roadmap. Where am I going? What do I have to do to solve this problem? I got to convert grams of aluminum oxide to moles of aluminum oxide and then convert that into moles of iron oxide. So let's do that. So we're right kind of where we were on the previous problem. Same molar mass, nothing's changed. Aluminum oxide is 101.96 grams per mole. I didn't need grams per mole right there. I got the mole up here. Grams per mole there. So that gets me to moles of aluminum oxide. And look at this. There's 1 mole of iron oxide for every 1 mole of aluminum oxide. Now that stoichiometric factor doesn't change the number at all, but I don't ignore putting that in there. If you kind of just say, oh, I don't need to put that in there because they're both 1s, the next time you forget to use the factor, okay? So use the factor all the time, even though it's 1 to 1, 1 times any number is that number. It's not going to change the number, but it does convert moles of aluminum oxide into moles of iron oxide. And what did you get in the answer?
198.
All right. And, you know, label your answer. What do we got right now? 0.498 moles of aluminum, of iron oxide. Okay, now part D, what can you do to simplify part D? Use the answer to part C. So start right here. Did you all get 4.498 or 0.497 or 0.98? Rounded off to 0.498. Okay. So you got moles of iron oxide. And how do we go to grams of iron oxide? What's the magic number we need? Okay, you need the molar mass. I didn't point that out up here. Maybe you all calculated, but someone already got it up here. So it's 159.7 grams of iron oxide. Is that what you get? Per mole of iron oxide. And how many grams does that come out to?
9.5 grams.
All right. All right, so let's help me with these numbers now. This has problems A, B, C, and D, and we got problems A, B, C, and D here. You have these two slides right next to each other. So, part A, determine the number of moles. What did we say that was? What's the answer to part A?
0.99.
Part B,
26.1 moles.
grams. Daniel, the unit right there now is just grams, okay? Because we're not saying it's grams per mole. It's actually grams per 0.996 moles, right? Because that's what we calculate. That's what we're figuring out there. We're saying how much does this weigh? Weighs that. So don't put the unit of grams per mole here. This is just simply grams. This 26.98 is grams per mole. That's what we get off the periodic table, because that is the mass of exactly 1 mole of it. This is a real close number. This is a real close number, but it's just that amount. This one was 0.498 moles of aluminum oxide, and it was what was 79.5 grams of iron oxide. This is your theoretical yield of iron oxide. This is your theoretical yield of aluminum. Oh, that's aluminum. I'm sorry. This is confusing enough with me mislabeling things. Okay? Does that summarize it? That's what we calculated so far? Okay, now look at E. If the actual yield were 20 grams of iron oxide, calculate the percent yield. All right, so this is a percent yield. I've got some good news for you after we do this calculation. Let's just do it though. Well, let me give you a real practical example of theoretical versus actual. What is the theoretical capacity of this room? How many students can sit in this room? Now, just figure the tables. We've got 4, 1, 2, 3.
28.
All right, so there's 4, 4, and 4. That's 12, 13, 14, 15. 15 tables. All right, so we have 15 tables times 2 students per table. So we have a theoretical capacity of 30 students. How many students are here right now? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We've got 19 students here. So what's our actual, not capacity, but attendance? We've got 19 actual students. See, you're actually one of them. Actual students here. And there's room for 30. Theoretical. So what is the percent capacity in this room right now? 19 divided by 30 times 100%. 63%. All right? Okay, you see what I'm talking about? We have room for 30 students, but we don't have 30 students here. All right, so let's go up to this one. We could, with that 50.8 grams of aluminum oxide, we could make 79.5 grams of iron oxide. Everything went perfect. But it says, okay, we did it, we got the iron oxide, we weighed it, and we only actually got 20 grams. So percent yield is actual divided by theoretical times 100%. So our actual is 20. Our theoretical is 79.5 times 100%. And now notice on dimensional analysis, those units cross out. Grams of iron oxide in the numerator and denominator cross out. We're going to just get 8%. It's a percent yield. What's our percent yield? What is it, Daniel? 25%? 25.0?
25.1. 25.2.
25.2% yield. Follow that? Okay. You have a homework assignment on theoretical and actual yields. We did that calculation. Now here's the good news. I'm not going to put this calculation on the exam. Okay? Do the homework assignment. Do the quiz associated with it. Why would I do that? I want you to be familiar with the terms. I want you to be familiar with the concept. If you took a TEAS test or something and they were asking you to do that, you would say, I never even heard of this. Well, you've heard of it, and that's it. Right down through here definitely is going to be on the exam. A, B, C, and D.
One of the easy ones, not going to be on the
All right? So the stoichiometry problems, yes. And usually when it says how much can be produced, it's asking theoretically how much can be produced. What could you possibly get out of this reaction? All right. Let me make a few more comments. I know this is kind of far away for Mark especially, but let me talk a little bit about the exam. I don't have the exam finished now. I started working on it last night, but I think where it will land is about 50% will be multiple choice and 50% is going to be problems. It's not going to be, so there may only be about 25 multiple choice questions, and then 50 points is going to be this sort of stuff. I probably will give you, I would think I'm going to probably put about 5 equations on the board, chemical equations, and say balance these equations. You could expect one of them to be a combustion equation. So that'd be probably 2 points each for those, 10 points. I'm going to probably put 2 stoichiometry problems like that, and they'll probably each be 5 points each. So there's another 10 points. Molar mass will be mixed in here. You'll have multiple choice questions. They'll say, you know, the molar mass of magnesium nitrate is A, B, C, or D, and or E. You'll have to figure it out and then choose the right answer. It's fair game. We haven't done a lot of it in class, but to convert moles to number of atoms. If I said I had 7.98 moles of helium, and I wanted to know the number of atoms of helium that are in there, how do I do that problem? How do I convert moles into atoms? Avogadro's number. There are 6.02 times 10 to the 23rd helium atoms per mole of helium. That number does not change. Okay? I mean, sometimes we use more significant figures than this, but the number basically doesn't change. And it doesn't matter whether I'm asking about atoms or molecules. If I said I had 7.98 moles of water, and the question was, what is the number of molecules of water? You see, we change this word here depending upon what we're talking about. If we're talking about a molecule, then we say how many molecules are there. If we're talking about discrete atoms, we say how many atoms are there. But the number does not change. There are 6.02 times 10 to the 23rd molecules of water per mole of water. Okay? That does not change. 1 mole is what? It's that many things of whatever you're talking about. Because remember, a mole is a number, like dozen. You don't sometimes change dozen to 14. Dozen always means 12. Mole always means that number. Okay, so there may be a couple of these in there. Module 6, I'm not going to lean heavy on Module 6. There may be 4 or 5 questions in here that says here's a chemical reaction. Is it an acid-base reaction? Is this a precipitation reaction? Is it a combustion reaction? Something like that. Might ask you to classify. It should be pretty obvious. And then conversions. I mean, you should be able to go from centimeters to inches. You should be able to go from well, let me just say this. If you were asked if you had something like this, 26.5 kilometers, and it says how many millimeters is this? All right, remember, kilometer is a big number. There's that equals 1,000 meters. A millimeter is a little number. It is 1/1000th of a meter, or 10 to the minus 3rd meters. Well, what's the common unit in here? Meter. So when I do these problems, I don't have a conversion factor that goes from kilometers to millimeters, but I do know the relationship between millimeter and meter, I know the relationship between kilometer and meter, so do it that way. Let's convert this to meters. There are 1,000 meters per kilometer. And then let's convert this into millimeters. There is 1,000 millimeters per meter. I mean, that's another way of saying this. A millimeter is 1/1000th of a meter, but there are 1,000 of them in a meter. Here's a meter. There are 1,000 little lines on there. Each one of those lines is a millimeter. Do we need to hand this around? Pass this around? Okay. See all the little lines on there? It's first divided into 100 centimeters, and every centimeter is divided into 10 millimeters. There's 1,000 millimeters in a meter. But you see what I'm doing? I'm going from kilometers to meters to millimeters. This is a metric to metric conversion. Could have the same sort of thing going from liters to milliliters, whatever. So just, kind of, Newton, I hope, touched on some of these things. I was admitting earlier, I haven't had the time to do all these Newton homework assignments. I had time to assign them. I didn't have time to do them all. I probably shouldn't go on the record for that. But I wanted to get in and do this stoichiometry, or at least see this stoichiometry homework assignment. So I'm counting on Newton. I told you this is our first semester doing it. I'll become more and more familiar with it, perhaps with time. But this is driving you into things and practicing things. All right. This was the important thing here. So don't forget temperature conversions, density. Keep in mind, the periodic table is going to be really, really critical to you in this exam because of all the stuff on the back of it. So get familiar with what's on the back here, the conversion. The conversion units you have, how to set up a conversion problem. And then, of course, for molar masses, right here. And sometimes you might be asked, what's the molar mass of platinum? All right, right off the periodic table. Platinum, 195.08 grams per mole. That's its molar mass. It's not a compound. It's an element. If you were asked the molar mass of bromine, okay, now that one gets a little bit confusing. Why? Bromine. The question might have to specify some things, but what do you know about bromine? How does it exist as an element?
Blue one.
It's a blue one? Yeah, you know that.
It's a liquid at room temperature.
It's a liquid at room temperature, and it is diatomic. It's a diatomic element. That's instructive here because, well, I mean, if I asked you what is the molar mass of oxygen, I mean, technically, I should maybe say, am I talking about oxygen atoms or am I talking about oxygen molecules? But if I'm talking about the element oxygen, it exists that way. I'll take bromine out of there for a second because we're a little bit more familiar since we're all sitting here breathing. Are we all breathing? We're all breathing. I kind of knew that. We're all breathing this. We're familiar with that. So the molar mass of this is 32. All right? So even though it's just oxygen, there are two of them attached to each other. So its molar mass is 32 grams per mole. And that would be the kind of way you'd have to deal with any of the diatomic elements. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. That's it. Okay? These 4 halogens, those 2, and that's what's in our air, is nitrogen, N2 and O2, and then hydrogen gas is H2. So their molar masses you have to multiply by 2.
So when they give us a question, what's the molar mass of the element oxygen, we should know that it's 2 oxygen.
That it is O2.
Is O2.
The formula is O2. And I mean, when we do these kinds of problems, you can see we're entering oxygen not as O. We don't put O in there. We put it the way it exists as an element, O2, diatomic. All right. So if you balance this equation and you wanted to know how many grams of oxygen were produced, you're going to have to work off of this molar mass of oxygen to get the grams of oxygen produced. Yeah, I mean, you'd have to balance that equation first. Okay, we've got 25 minutes. So you help yourself now by asking me questions. I'm wondering, I'm not sure if I have the answers to these. What would you like to address? You can kind of see what's on the exam. I told you I didn't I didn't make up the exam yet, and I'm not going to necessarily guarantee you that's the only thing on there, but off the top of my head, these are the main elements. I'm going to take a picture of this and make sure I kind of stick with this. All right, and I won't put a theoretical yield problem on these.
Okay, so you said for the types of reactions, so will we only need to know like if it's a decomposition, combustion, or like what would we need to know for the types of reactions?
Well, certainly acid-base, be able to recognize an acid-base reaction, be able to recognize a precipitation reaction, and combustion. This is combustion.
Carbon, hydrogen, and oxygen.
Yeah, basically when you're burning something, that would be a combustion reaction like this. Yeah, burning something. Decomposition, and I'm going to see if I can pull up this list of reactions right here, and maybe we can run down through and.
What I had the most trouble with was like the acid-base and gas reaction, the
Yeah.
oxidation, and the ionic reaction.
Okay, let's see if I can find this
I just didn't like how you taught
worksheet.
that one.
The types of reactions. Where did these worksheets go? Can't find my worksheets. I put so many slides in here, but now I don't know where to find the worksheets. I suppose best thing to do is maybe call them up. Where's that? Let's see if I can call this up. I put these things? In class worksheets. Do I have them right here? Balancing equations. Oh. Yeah, there we go. Okay, for example, here is an example of a decomposition. Okay, this is an example of decomposition. How do you know that? Well, there's only one thing. There's only one reactant. All right, and so that's kind of a sign that you got a decomposition going on here. I'm talking about the KClO3 going to KCl and oxygen. It's decomposing. Let's see if I can find another one. Here's some combustion ones, obviously, pretty obviously. So reacting with oxygen, producing carbon dioxide and water, that's combustion. Let's see if I've got any acid-base reactions. I don't see them here. Precipitation reactions. The critical thing to look at there, I'll put up one that you are familiar with, at least some of you in the lab. If you remember this one, you would see it this way. Okay, what is all this telling you? Well, this is telling you that this potassium iodide is soluble in water. It's a solution in water. The lead nitrate is a solution in water. To put an AQ right there means that that will dissolve in the water. It will form a solution. But then to put an S right here, if you mix these two things together, you're going to get a precipitate. This is a precipitation reaction. This is indicating that the lead iodide is not soluble in water, and it's going to fall out of the water. So this is your critical indicator here, that you're dealing here with a precipitation reaction in an aqueous environment. And where is the potassium and the nitrate going? It's still floating around in the water. It's soluble in water, yes.
So like on the exam, when you had the symbols on it,
yes.
So we could be able to tell.
Yes, I'd have the symbols. I don't know that I'll have symbols on every equation there, but it's certainly if it's a precipitation one. In other words, if you look back here at this here, you can't just look at this and tell. There is a way you can figure this out. You would have to go look at that solubility chart. I'm not going to get involved in that in the exam a whole lot. But that's where you would look at those solubility rules, and you'd say, the halides are generally soluble in water. Sodium iodide, potassium iodide, magnesium iodide, calcium iodide, they're soluble in water, except lead, silver, and it'll put the exceptions out there, and this is one of the exceptions. Lead halogen compounds are not soluble in water. Yes?
Okay, so if there was two aqueous solutions and they produce a solid and an aqueous,
that would be a precipitation reaction.
is it always like that, or does it change? So with it, like for what it produces, can it produce a gas in an aqueous?
going to be a precipitation.
It's always gonna be solid?
Yeah, it's always going to be a solid. Where you're producing gas, that's probably something else, oxidation reduction or something. Gene?
So is precipitation also called exchange?
Is what?
Also called exchange?
Yeah, that would also be a double exchange or a double replacement reaction. Yeah, and that's probably what Newton got into, some different ways of talking about the same equation, same reaction. Yeah, this is taking potassium's place, and the iodide is taking. Then that's your double replacement. They're switching places. Okay, acid base. Acid base. Look for something like this. Okay? Look for something like this. What's an example? What am I talking about? HCl plus potassium hydroxide is going to produce water. And what else? What else will this produce? And what's salt? Fill in this last blank right here.
NaCl. Salt.
What? KCl. Joel? Just because we said salt, it has to be KCl.
All right.
All right? There's no Na in this side of the equation. So it can't produce NaCl. It has to produce this particular salt, KCl. And how are we figuring that out? Well, look at what is missing. What is on this side of the equation that isn't here? All right? Again, I'm going real easy on you. We didn't drill on how to finish a chemical reaction. I'm giving you completed chemical reactions. 5 cases, I'm going to ask you to balance them. 2 cases, I'll give you a balanced chemical equation and ask you to do a stoichiometry problem. Okay? So on the stoichiometry problems, the equation is going to be balanced. I got to be careful that I don't give you one of the equations and I'm balanced. Okay? Be careful. Sometimes that happens. You have to find the answer to one of your problems on the exam. So the smart student does that too.
So in an acid-base reaction, for the whatever it produces, you look like it's not there?
Yeah.
So like the potassium and the chloride?
Right. So this ends up being the salt. And where did we get the water? You know, we're getting the water from the hydrogen that's in the acid and the hydroxide that's in the base. And so for an acid-base reaction, hunt for an acid, some H-containing compound reacting with some OH-containing compound, and it produces water. That is an acid-base neutralization reaction. The acid is being neutralized by the base. Okay, pay attention to your emails or Canvas. If you see that something changed on Canvas, go see what changed. Because if I can find the answer sheets to these, I'll post them up on Canvas. All right, so that I want to encourage you to dig in here and try to do these, and then try to find the answers. If I have the time, and I can't find the answer sheets, I'll try to fill some of these out. And if I don't have time to do it all, I may do a couple of them and slam it on in there so you can see. Yeah. No. The test, the first test, I wasn't here that week. Okay. So this second test will be on Thursday at 8 o'clock right here. It will be an hour and 20 minutes. If you want an hour and 30 minutes, then get here at 10 to 8. All right? If you come in 10 minutes early, I'll let you get started on the exam. Bring a Scantron. Bring a Scantron. It won't be on a computer. It'll be on a piece of paper. I will give you this, okay? I'll give you this. So don't feel like, oh, I can bring my periodic table. I restricted to this because I want everybody to have the exact same information. No more, no less. Okay? So bring a calculator, a pencil, a Scantron, and a good night's sleep, and be ready for the exam 8 o'clock on Thursday. Yeah, it'll be right here. I'm glad you asked that question because it's kind of confusing. No, that first test was a outlier. I just wasn't here, and that's how we handled it. But we'll all take this one at the same time on Thursday. Okay? Good. Good question. All right. Study. Do problems. The more problems you do, the better. Just do problems. Rounding. That's my abbreviation. I rounded it off. Dimensional analysis. That's where you have like this, and you're multiplying this by inches per centimeter. Dimensional analysis.
So, lab.
You don't need to do it until next week.
So if you already did, then
I bumped it up so that you can do it again. Okay? So you'll get another attempt to do it.
Okay.
After the lab.
So are we still doing that same lab?
Yeah, we're doing that same lab today.
Okay.
And I'll tell you. Let me stop this thing.